It's hard to imagine the modern world without the internal combustion engine. It's used to drive such a vast variety of machines, including, of course, the car. It was the invention of the engine that made the whole idea of the car possible. The principle on which it works is really quite simple. It's really just like a cannon, the explosive fuel forcing out whatever's inside the barrel. This is actually a firework mortar, and it forces out this cylindrical shell, and the explosive fuel is the gunpowder in the bottom. Put it in here. The internal combustion engine is really just the same, except it has a captive piston instead of the shell, and it uses an explosive vapour instead of the gunpowder. Although the idea is very simple, it hasn't been easy to tame the violent energy of all these explosions thousands of times a minute. In this programme, I'm going to look at this wild, unlikely contraption and also at its fuel. Almost all internal combustion engines use a fuel based on crude oil. This naturally seeps out of the ground in places and has been known about since ancient times. It had a variety of uses, but not as a fuel. It's mentioned several times in the Bible. Noah was instructed by God to use it for waterproofing his ark. It was only in the 19th century that oil's potential as a fuel was realised and people started drilling and refining it. One of the products of the refining was a volatile gas oil, or petrol. The petrol was at first regarded as a completely useless byproduct. Its vapour was so dangerously inflammable. But it was also realised that it was an enormously potent source of energy. We can show you this with this modified firework mortar. This obviously isn't an experiment to do at home, but if Rex puts a teaspoonful of gunpowder down the mortar and using the lager can as the projectile, oh dear, well, it is not very powerful. Well, now we're going to compare this with a teaspoonful of petrol and see how far that goes. This time we're igniting it with a spark plug in the side. You can see what an enormous amount of energy there is in the petrol. Although it's hard to believe, this isn't actually an explosion. It's just a very rapid combustion, a very rapid fire. The early internal combustion engines were often called explosion engines, though, and I think it's really a much more appropriate name. The great attraction of the explosion engine is the enormous power it has for its size and weight. This is the smallest engine we could find, complete with fuel tank behind, used for model aeroplanes. Even this has enough power to pull Rex round at quite a speed, though it takes a bit of time to gather momentum. The power of any modern car engine is quite awesome. Even a basic one is rated at about 60 horsepower. That's literally equivalent to the power of 60 horses. The first successful explosion engine was built by an inventor called Etienne Lenoir in 1859. He simply threw away the boiler of a steam engine and modified it so that it would ignite the piped gas supplied for lighting. Unfortunately, the violence of the explosions tended to damage the piston and valves, and it was much less efficient than the original steam engine.
Ooh, sit down.
Mais monsieur, qu'est-ce que c'est que ça? Oh, ça suffit, ça suffit, alors de la nuit, hein.
However, His engine inspired other inventors, including a German wholesale grocery salesman called Nicholas Otto.
What is los? Herr Otto. Enchanté. Oh, Himmel!
Otto came up with an engine that was much more efficient. His engines were immediately successful, and he sold over 35,000 to power factories and workshops. One of the first Otto engines to be built in Britain was the 1895 Hornsby Ackroyd. It all still looks very like a steam engine, but it runs on paraffin, another product of refining crude oil. It first has to be heated to make it an inflammable vapour. It's a two-man job to start it, and it never goes round faster than 100 times a minute. What's going on inside is that first the vapour is sucked into the cylinder. Then it's compressed, ignited, and finally the exhaust gases are pushed out. This sequence, suck, squash, bang, blow, is called the four-stroke cycle. Otto's big improvement was squashing the vapour up before igniting it, which gave the engine much more power. Although from the outside a modern car engine looks completely different, and it's obviously got more than one cylinder, inside it's really quite similar. If you can start turning it over. The piston goes in and out. The crankshaft goes round and round. And this is the exhaust valve with the strong spring keeping it closed and the cam pushing it open. The other valve, the inlet valve, is tucked away behind on this engine. The rusty space around the edge is full of water, essential for cooling the heat of the explosions. All these fundamental features have remained unchanged. Otto's engines were much too large and clumsy for a car, but one of his employees, called Gottlieb Daimler, developed a much smaller engine in 1883. This ran much faster and used the volatile petrol as the fuel. It produced nearly as much power as Otto's, but weighed 10 times less. Daimler's high-speed engine finally made the idea of a car practical, and it was quickly realised that cars could do some quite remarkable things. The early engines did still have their drawbacks, though. This is a 1902 Wolseley owned by Jack Howes. Under the bonnet really just contains the enormous cooling system and radiator. The engine's tucked away right underneath. It's not entirely easy to operate. There are 20 operations you have to do before you can start it. Where do you start?
First thing I do is to connect the battery, then I turn on the petrol tap and just give the carburettor a touch to draw the petrol through. My next operation after that is to turn on the 12 oilers for the total loss oiling system. Now the most important job of all, having inserted the starting handle, as you can obviously see, the side of the engine, is to put it on half compression. Otherwise there's a great risk of breaking your wrist. Turn on the switch, adjust the throttle and ignition controls.
It's not just tricky to get it going. There are two levers controlling the fuel and ignition that have to be skillfully adjusted as you drive along. One false move and the thing stalls. Also, the engine's very inefficient by today's standards, only doing about 12 miles to the gallon. And the total loss oiling system leaves a trail of oil along the ground wherever it goes. Engines haven't changed radically since this time, but their design has been continuously refined. Arguably, the biggest single improvement has been in the oil and how the engine puts it to use.
An engine wouldn't last for long without oil. The oil's fed through holes in the castings to all the bearings. There's actually an enormous amount of oil being pumped round all the time. I can show you this if I knock a hole in the oil filter. This may be a bit messy. The oil doesn't just lubricate, it all gets rather black and filthy like this, because it's also a detergent.
It cleans up the deposits left by the exploding gases. Before this detergent was added in the 1940s, you had to strip down the engine and clean everything out, or decoke it, every few thousand miles. Now you just have to change the oil and the filter.
I'm going to turn it off, actually.
Many of the improvements in oil and petrol have been made possible by more sophisticated refining of the crude oil. Today, almost everything a refinery produces can be used by the car industry. Besides petrol and oil, it provides the chemicals which are the basis of plastics, paints and synthetic rubbers, and even the bitumen that the roads are made of.
Gasoline, liquid power to run millions of automobiles everywhere. Yet, how many know what happens to the gas after it is poured into the gas tanks, or realize the care that motor car engineers have taken to give each drop an equal chance to do its duty? Gasoline is powerful, but each drop can give a 100% account of himself only when he finds the most efficiently designed gasoline system to help him along his journey. For a successful life, every drop of gasoline depends entirely upon what happens to him after he gets in the swim.
First, the fuel has to be mixed with air. The air comes in through the large air filter on top of the engine, and it's mixed with the fuel inside the carburettor. It's easiest to see the principle of the carburettor with this model. We've used a vacuum cleaner to represent the engine because it's sucking in air all the time. It simply sucks the fuel up and mixes up this little tube and mixes it with the air in here. Here we're going to use red ink instead of petrol so that you can see it more clearly. Petrol by itself isn't explosive, only the mixture of petrol vapour and oxygen from the air. You can see the petrol being sucked in looking down a real carburettor. Unfortunately, real engines need different concentrations of fuel for different conditions, starting, idling, accelerating, etc. That's why the 1902 Wolseley had the mixture lever on the steering wheel. Modern carburettors make all these adjustments automatically, but this is why they're so fiendishly complicated. Today, a completely different system, fuel injection, is becoming more common. It's basically very simple. There's just a row of electric valves, one for each cylinder, that squirt a bit of petrol into each inlet. The precise length of time the valve opens, controlled by a computer, varies the amount of fuel injected very accurately. Once the fuel and air has been sucked into the cylinder and squashed up, it's ignited. The spark's created by a high voltage jumping across a gap in the spark plug. The high voltage itself is created by the coil connected to the battery. Engines don't like getting wet because water provides an easier path for the electricity than jumping across the gap, which I think I can show you. Put the spark out. Fortunately, though, you can often get the spark back again simply with a water-repelling oil. Although the ignition should be started by the spark, petrol's a complicated mixture of chemicals, some of which are quite unstable. These can ignite spontaneously under heat and pressure, causing a sort of uneven explosion called detonation or knock. As engines have become more powerful over the years, knock has become more of a problem. It can be overcome either by damping the unstable compounds with lead additives, or in lead-free petrol by refining the unstable compounds out. The other option, used in diesel engines, is to refine the fuel less and to compress it more. The more the fuel squashed up in the cylinder, the hotter it gets. It can get so hot that it ignites spontaneously without any spark. We've blocked the bottom of this cylinder up completely and cut a hole in it. And if I put a bit of fuel in the side here and bash the piston down with a hammer, it should ignite. If I blow out the burnt gases, there may be enough fuel left to make it work a second time. It was a Victorian cigar lighter working on this principle that inspired Rudolf Diesel to design his first engine in the 1890s. Diesel believed that more compression would make his engine much more efficient.
A vision I have of a better future. Machines will free mankind from slavery of work.
The higher compression made the engine more dangerous, and a prototype nearly killed him.
What? Nearly killed me.
By 1895, though, Diesel had a design which ran on cheap fuel and was twice as efficient as any other engine of its time. Diesel became a millionaire from his invention, but invested very badly, quickly getting heavily into debt, and decided he couldn't carry on.
Ah, my God! I cannot pay this!
In May 1913, he set off on a night ferry to Britain.
I go. Goodbye.
He was never seen again. Today, the diesel engine has been greatly improved and it's now fitted in many cars. This contraption, which Rex and I built for a TV series a few years ago, is diesel-powered. The engine, from a Volkswagen Golf car, hardly looks any different from a petrol one. However, as Diesel originally thought, the higher compression does make the engine more efficient and do more miles to the gallon. Here, as well as driving the vehicle, the engine's also powering the hydraulic lift. The most dramatic change to both diesel and petrol engines in the last 10 years has been the addition of sophisticated electronics.
This modern car engine, compared to the earlier ones, is horrendously complicated. For example, there's two computers on board. One controls the electronic fuel injection and another one controls the cruise control. Even though the engine is much more complicated, this makes the most of every drop of fuel and gives greater fuel economy and power. Although the complex electronics would be impossible to repair by the roadside, I've driven 80,000 miles in it, and even with my poor maintenance, it's never even failed once.
The engine's improved enormously since 1900. It starts at a flick of a switch. It's incredibly powerful. And it's really very reliable. But it's still far from perfect. Despite its power, it's really very wasteful. 4/5 of the energy released by the petrol is simply lost as heat through the radiator and the exhaust. And the exhaust gases themselves pose even worse problems. There's an awful lot of them.
The average car releases 4 times its own weight in exhaust gases during its life. And it's all pretty horrid stuff.
This wasn't such a problem when there weren't so many cars around.
If we are to realize in full the motor car's vast potential for good, we must use it and care for it wisely. The motor car has been the key to open new horizons, not for the few, but for all. And all of us share in the responsibility of safeguarding the benefits it has brought. If we plan for the future, if we look ahead to clear all obstacles and roadblocks, if we recognize the importance of this great individual freedom of movement, the motor car will be the key to our ever-widening horizons of tomorrow.
If you want to sing about America, you'd better make sure you have the breath to sing with. We've been fighting air pollution, but it's time to fight harder. Help us. It's a beautiful country. Let's not get all choked up about it.
In an attempt to clean up the exhaust gases, catalytic converters are gradually becoming compulsory all over the world.
Oh, Dad! Dad, it smells all funny! Dad, stop!
Recent reports from America suggest in practice catalysts may only remove about 30% of the poisonous gases because the engine needs careful maintenance for them to work properly.
Oh, not to worry, sir. Trouble with the catalytic are very common these days. I'll just adjust this screw and then that'll be all right.
Even when they do work perfectly, they only convert the gases to carbon dioxide, the greenhouse gas.
It's getting awfully hot, dear. I'm boiled, Dad!
Nothing for it. We'll have to go electric. It's the only way to be really green.
Electric cars aren't perfect either. The electricity to charge their batteries just transfers a lot of the pollution to the power stations. I don't think there's any such thing as a completely green car.
The engine's really a victim of its own success. Despite its disgusting exhaust, it's such a reliable and potent source of power, it's made the car and all sorts of other machines completely indispensable. It's so central to our modern way of life that there's almost something rather religious about it.